quantum mechanics does not indicate the existence of no-cause events. One common misconception is that quantum mechanics suggests that some events occur without a cause, contradicting the classical principle of causality. Here, I will show that quantum mechanics does not demonstrate the existence of no-cause events, and that the indeterminacy at the quantum level does not negate the need for underlying causes. Causality in classical physics versus quantum mechanics. In classical physics, events are typically understood in terms of deterministic cause and effect relationships. Newton's laws of motion, for instance, allow for precise predictions about the behavior of objects given their initial conditions. If we know the force acting on an object, its mass, and other relevant parameters, we can predict its future motion with great accuracy. This reflects a classical understanding of the universe where every effect has a preceding cause. Quantum mechanics, however, operates differently. The behavior of subatomic particles such as electrons, protons, and photons is governed by the probabilistic nature of the wave function. This probabilistic framework has led some to suggest that quantum mechanics entails a breakdown of causality, with events like the decay of radioactive particles or the appearance of virtual particles in a vacuum happening without a cause. But is this interpretation correct? I would show that it is not. Quantum indeterminacy versus causality. Quantum mechanics does introduce an element of indeterminacy, most famously captured by Werner Heisenberg's uncertainty principle. The uncertainty principle states that certain pairs of properties, like position and momentum, cannot both be known to arbitrary precision. This has led to the idea that quantum mechanics does not offer definite outcomes but instead provides probabilities for different outcomes. This indeterminacy is sometimes confused with the notion that events occur without causes. However, the indeterminacy in quantum mechanics refers to our ability to predict specific outcomes, not to the absence of causal processes. For example, in the case of radioactive decay, we cannot predict exactly when a particular atom will decay, but we can predict the statistical likelihood of its decay over time. The probabilistic nature of quantum mechanics represents a limitation in our knowledge of exact outcomes, not a breakdown of the cause and effect relationship. In fact, quantum mechanics is governed by strict mathematical laws, such as the Schrödinger equation, which describes how the wave function evolves over time. While quantum outcomes are probabilistic, the processes that lead to these probabilities are deeply embedded in the causal framework of quantum theory. The probabilistic outcomes are not uncaused, but rather the result of complex causal structures that govern the interactions of quantum systems. Quantum fluctuations and vacuum energy. One of the most frequently cited examples of supposed causeless events in quantum mechanics is the phenomenon of quantum fluctuations, where particles appear to pop in and out of existence in a vacuum. This is often presented as an example of something coming from nothing, and is used to argue that quantum mechanics undermines the principle of causality. However, this interpretation is mistaken. Quantum fluctuations occur within the context of the quantum field, which is itself a structured and well-defined entity. The vacuum of space, as described by quantum field theory, is not truly nothing. Rather, it is a seething backdrop of potential energy where fluctuations are possible. The appearance of particles in a vacuum is not uncaused. Rather, it arises from the properties of the underlying quantum fields, governed by precise mathematical rules. So, quantum fluctuations do not violate causality. They occur within a structured and rule-governed system, and while we may not be able to predict the exact moment a particle will appear or disappear, these events are not without cause. They are caused by the interactions and properties of quantum fields, which follow their own inherent laws. Misinterpretations of quantum mechanics. Many of the misconceptions about causality in quantum mechanics stem from misunderstandings of what quantum theory actually says. It is important to distinguish between indeterminacy and a causality. The indeterminacy of quantum events reflects the limits of our predictive power, not the absence of causes. Just because we cannot predict the precise outcome of a quantum event does not mean that the event lacks a cause. The cause is in the complex underlying interactions of quantum systems, and the outcome is fundamentally probabilistic, but probabilistic does not mean uncause. It is also worth noting that several interpretations of quantum mechanics, such as Bohmian mechanics, also known as pilot wave theory, are fully deterministic. Bohmian mechanics suggests that quantum particles follow deterministic paths guided by a wave function, even though we can only observe probabilistic outcomes. In this view, quantum mechanics retains a causal structure, and the apparent randomness is simply a reflection of our ignorance of the full system. The limits of scientific knowledge. Another important consideration is the distinction between the limits of human knowledge and the nature of reality itself. Quantum mechanics reveals that there are limits to what we can know about the precise behavior of particles. However, these limits on knowledge do not necessarily imply limits on reality or causality. In philosophy, this distinction is often referred to as epistemology, the study of knowledge, versus ontology, the study of being. Quantum mechanics may impose epistemological limits, meaning that there are certain things we cannot know about particles and their behaviors. But this does not entail an ontological conclusion that the particles themselves are uncaused or indeterminate in their existence. Causality and the existence of God. The idea that quantum mechanics undermines causality has sometimes been used in arguments against the cosmological argument for the existence of God, which asserts that everything that begins to exist has a cause. If quantum mechanics demonstrated that events can occur without causes, it might seem to challenge this principle. However, as we have seen, quantum mechanics does not in fact demonstrate the existence of uncaused events. The indeterminacy of quantum mechanics is consistent with causal principles, albeit in a probabilistic framework. Moreover, quantum mechanics operates within the context of the universe's laws and does not address the ultimate cause of the universe itself. The Kalam cosmological argument, which concludes that the universe must have a cause, remains intact because quantum mechanics does not offer an escape from the need for a cause of the universe as a whole. Conclusion. Quantum mechanics is a powerful and fascinating theory that reveals the complex behavior of particles at the smallest scales. While it introduces indeterminacy and probabilistic outcomes, it does not indicate the existence of uncaused events. Instead, quantum mechanics operates within a framework of cause and effect, even if the causes are probabilistic. Misunderstandings about quantum mechanics do not invalidate the principle of causality, which remains a foundational concept in both science and philosophy. Far from negating causality, quantum mechanics continues to operate within a causal structure. The idea that everything that begins to exist has a cause is as valid in the quantum realm as it is in the classical world, and it continues to provide a strong foundation for arguments about the nature of reality and the existence of a creator. Thanks for watching. Please like, share and subscribe, and comment below if you agree or would like to add your thoughts. If you would like me to respond to your comment, please make a level 1 comment directly below the video. I will respond to all polite level 1 comments even if it takes me a while, due to other commitments.